says classify these molecules as polar or nonpolar. So that's number 3. It's polar. Let me just make a T-chart here. Actually, no, I'll just leave it. I'll just leave it here. Polar versus nonpolar. Okay, so when we talk about polar versus nonpolar, we're talking about this difference in either dipoles or the difference in electronegativity. So in order, if we have a positive end and a negative end here, then this atom is polar. For example, if I drew HCl here, and I have a very extreme dipole, I have a dipole between this hydrogen bond, chlorine bond, right? I have a positive, I kind of have a dipole negative or a partial negative here in terms of chlorine, because it's taking away, it's the more electronegative ion here, and hydrogen here would be a partial positive, right? So this here is an example of a dipole here, depending on the electronegativity difference. So in order, when we talk about this concept of polarity, we're talking about this concept of non-bonding electrons. So let me look, I'll take water for example. So we have water first. I'm going to draw H2O here. And water here is a polar molecule. Why is water a polar molecule? Well, we have these lone pairs on hydrogen here. These two lone pairs, these electrons, actually let me draw this in red, maybe make it easier for you to see. These lone pairs here on hydrogen here are not being bonded to anything. And if it's not being bonded to anything, these are going to basically repel and create this bent structure. That's why water here is a bent structure, right? It's not a it's not kind of a triangle like you expect, or a linear molecule like you expect. These electron lone pairs are actually pulling electron density towards these lone pairs here. So it wants space and wants to create that space here. So given that, this here would be a polar molecule, because I have lone pairs that exist that push and change the geometry of water here. So this here is a polar molecule. Next, I have H2. So H2 is simply just hydrogen gas. If I were to bond it here, it simply looks like this. And H2 here would be a non-polar substance, and because I don't have any electrons left, right? Hydrogen has one, and this hydrogen has one, and it's going to create this bond here, which has 2 electrons inside the bond here. And we don't have any lone pairs that exist here, which means this is a non-polar substance. So hydrogen gas is non-polar. Let's look at number 3 here. Let me just let's check here. So H2O is polar, good. H2 is non-polar, good. And let's see what they have here. So this is we want to know HF, which is kind of kind of like HCl here. If I draw HF as in terms of a kind of a Lewis diagram here, I have this bond here which has 2 electrons, but fluorine has 1, 2, 3, 4, 5, 6 here, right? These 6 electrons here are not participating in bonding, right? So electron here, electron here. These are all lone pairs. We have 3 pairs of lone pairs, right? So therefore, again, this here is a partial negative, and this here would be a partial positive here. Fluorine is the more highly electronegativity, and it's so the difference in electronegativity is so big. Therefore, this would be a polar compound. Polar compound, good. And then CH4, if I were to draw a carbon with 4 bonds here, do I have any lone pairs on carbon? I do not. These hydrogens are all bonded towards this carbon here. Again, carbon can make 4 bonds, and this here is completely satisfied, right? I have 4 bonds here, which means I have 8 electrons. Therefore, this has it's fully saturated. Therefore, this compound is nonpolar. I don't have electronegativity difference as well, because carbon and hydrogen are basically equal in terms of electronegativity. It's hovering about 2. BCl3. So this is boron trichloride here. This here is B. And boron here is also a nonpolar compound. And the reason why is that boron can make, again, 6 bonds here, or 3 bonds, sorry. And boron here is it's kind of a special molecule here, right? This here is it's kind of it has three valence electrons here. And what it can do is it can actually hybridize to form, boron can actually hybridize to form, to basically kind of create 3 bonds due to this, the 2p and 2s and 2p hybridization. So based on this hybridization here, where I can actually create kind of 3 bonds here. So based off that, that makes it, this creates kind of a flat compound here. So this would make it, this compound here, nonpolar. You could write out the electron configuration here, and you can say that this is 2s2 and 2p1. So boron here it's a 2s2 and 2p1. And basically, this here actually hybridizes it into an sp orbital. So basically, you would get something like you get 2 sp orbitals, and you would actually have three bonding sites. You have 1, 2, and 3. Therefore, chlorine provides. If I drew chlorine in red here, it would provide these electrons here to make this compound stable. So it hybridizes from 2 sp and 2p to a 2 sp hybridized orbital. Therefore, it fulfills the shell, and it would make this compound nonpolar here. So this here is BCl3, and finally CH3Cl. So you get something like this: carbon, bond hydrogen, bonding hydrogen, bond hydrogen, and this is bond chlorine here. Again, the carbon itself is satisfied. However, I do have electronegativity. I do have lone pairs. Sorry, I have lone pairs on chlorine here. So these lone pairs here will make it a polar molecule. It's drawing electron density away from the carbon here. It makes this carbon partial positive, and this is partial negative here. Thus, here, this is methyl chloride would make it a polar molecule. So I believe the answers here are correct. Okay, water here is polar, H2 is nonpolar, hydrofluoric acid here is polar, methane here is nonpolar, boron trichloride here is nonpolar, and methyl chloride is polar here. So great solution and analysis.